This is CPE 225. This is the first lecture of, we'll say, new material, sort of. It's not really, it's just really a course overview. And so let's grind through this thing. And a couple comments. This is CPE 225. It's sort of a lost course. It's not well defined. It's not well maintained, but it's part of the computer science department, courses they like to teach. So I'm here to do the best I can in this course. More comments on that later. I want you to realize that most of you are some type of software-oriented majors. Software runs on hardware. The word on the street is lots of times people taking this course do not like hardware, but you just got to know something about the hardware your program is going to run on. And if you do that, you will be a better programmer. Best programmers I've ever known were double E's. And the issue is they understand the underlying hardware. They understand the hardware that the program's going to run on. Helps them write better code. And by all means, they were kind of systems thinkers. They saw the big picture on this thing, and that helped them arrange and organize their code. And once it's arranged and organized, it was just more efficient code, ran faster, was less fragile, worked better, and all those amazing things. I encourage you understand, at least have some understanding of the hardware. I know it's probably not your thing, but I encourage you to do that. We're going to spend some time working with hardware in this course. This is my first time teaching this course. Materials are, other instructors have materials, but I didn't. I opted to, they had a different view of the course. I have my own different feelings about this course. I taught 233 probably 10, 12 times, which is essentially a similar course that the CPE, computer engineering, electrical engineering majors take. So at this point, I'm really not sure exactly what you know and what you don't know, what exactly you need to know. I'm taking a guess on that one, and where you have challenges, although people have said that the challenges are working anything with hardware, but you gotta work with hardware on this one. So I'm gonna make mistakes on this one. I don't really know what tools are optimal for and what tools we have on this one. I will be working with the other 225 instructors. I do have access to their materials, so I'll be working on that too. So anyway, I'm ready to do the best I can with this. So the course is Introduction to Computer Organization, and essentially a computer organization means computer architecture. Okay, it's just a more common term for computer organization. So the purpose of this course, as the best I can see it, is two things. It's to prepare you for CPE 315, but I was told, seriously, just a few days before, I generated these set of PowerPoint slides that CPE 315 is now optional for computer science majors. I'm not sure about software engineering, but it's kind of strange. So basically a computer is a bunch of submodules that do specific things, which isn't necessarily hardware. And we will be kind of needing to understand at least some of that to help us write assembly language programs. Assembly language is what makes the world go around on this thing. It's super important. It's, in my mind, it's so basic that it's very, very doable. It gets weird at first, but anyone who has programming experience can pick it up really fast, and I encourage you to be one of those people. The other thing for this course is I believe it's your first curricular experience in C programming. I know some people may have had it in CPE 1, 2, 3 if they in fact took that, but there's certain stuff I need to prepare you for 357. And I was told that 357 covers a lot of this stuff, so this is just going to be a basic intro to 350 to C, to help you hit the ground running in 357. My experience with C programming is on embedded systems, which is a little bit different than what we'll do in here, but it will be useful to I'll get you started on it. That's my promise for you. So digital, these digital circuits. So what we're going to work with is a digital circuit, and a computer is just it's a big digital circuit, not necessarily big. That's a relative term, but what this is a bunch of modules talking to each other, and there's a slide coming up on this one. So the computer architecture is a notion of the interconnection of those modules, and essentially it's a bunch of standard digital modules that I'm going to connect to form a computer. So a computer, what's a computer? You can get a lot of different definitions of a computer. I consider it a device that sequentially executes a stored program. So this is my digital circuit here, and what you see is a bunch of modules that are talking to each other. So on this left side here, you've got a bunch of inputs to this circuit. On the outside, the right side, you got a bunch of outputs. Typically, inputs are written on the left, outputs on the right. Not always the same, but these modules here, all I want you to take away from this is these modules are talking to each other, and by talking to each other, I mean they're exchanging information with each other under the control of something, and this one happens to be controlled by a state machine. So any computer, generally speaking, has a control unit in it. We don't get too far into that, but once again, what I want you to take away from this is a computer is a bunch of modules that are talking to each other, passing data between each other under the control of some other digital module, which in this case is a state machine. Generally speaking, in digital design, like this module here, I design it once and then I use it a bajillion times. Digital design isn't necessarily modular, like these boxes here are modules, and it's hierarchical. So I'm going to place all these boxes in another box, and I'm going to make that higher level box here into a box of itself, and I can use that also. So the computer, it's a device that sequentially executes a stored program. This is the accepted high-level diagram of a computer, and this is something you need to know. Essentially, there's a processor in there, which is the brains. There's memory in there, which it holds the program you're executing. Remember, that's a stored program, and the data. And then I need to talk to it. And the idea here is that's the data coming in and out of this thing. And that's why this arrows here. I mean, you can put these arrows are very generic, and essentially these modules are exchanging data with each other, just like in a typical digital circuit. I need to talk to the thing, and I need to have the circuit talk to me on this thing. So talking to its input, listening to it, seeing what it kicks out is the output on this thing. That's why this arrow has doubly directed. I forgot what the name of that is. So here's our basic model again, but I'm going to expand it a little bit here. I made the input-output module a module of its own, and I broke the arrows up for input going in, output going out. This is the brains here. It's a bunch of circuitry that is controlled by another circuit, which we refer to as a control unit. Essentially, you can see the control signals are controlling the other part of the circuit. CPU is generally the brains, ALU, arithmetic logic unit, which is a number crunching unit in this thing. The memory up here, it's generally speaking, it's instruction memory, which is the program you wrote. And then you have data memory, which is just, intermediate data that's going to help you, generate, solutions for the problem you're working on. Super important here. This is all the levels of programming. So typically, I know you've taken a prerequisite for this course, and you've written programs in a higher level language, so whether it be C or Java or what's the other one, Python, blah blah blah. So I know if you're in here, you've done this. The next level down is assembly language, and that's what we're going to be focused on in this class. And what happens is at this top higher level code gets compiled or interpreted, and it needs to generate some code that will run on your specific piece of hardware. Okay, so essentially that specific piece of hardware only understands a certain number of instructions, specialized instructions, and that's going to be the assembly code. So the assembly code, I'm going to write code. I'm going to feed it to a piece of software called the assembler. The assembler is going to kick out machine code. Okay, the machine code is a bunch of ones and zeros. On computer hardware only understands ones and zeros. So us humans have a little bit of trouble understanding giant sets of ones and zeros, etc., etc. So the sets of ones and zeros, which is the only thing the hardware understands, is called machine code. And I swear I'm going to do my very, very best not to work with machine code in this class. It's just pointless and grunt work, and it drives people away. I've never used it 233, and it's never been an issue. So we're going to be using RISC-V in this class as our computer architecture. There's a gazillion different computer architectures out there that we could be using. We're going to use RISC-V. It's relatively new, open source computer. It's super popular, super easy to use, not super complicated. It comes in a whole bunch of different flavors, and we're going to pick a flavor that's easy to use. Particularly, we are going to use RISC-V Otter, which is what we use in 233, and it's essentially a slightly modified instruction set than the typical RISC-V. And so we'll talk more about that later as it becomes more pertinent here. Okay, so we have a piece of hardware here, and the idea here is that piece of hardware only understands a certain subset of instructions, and these are essentially the instructions it understands, and that's it. That's all you get on this thing. And what you see up here is a set of mnemonics, and followed by some operands. So here's your mnemonic, and they're followed by operands. General makeup of assembly code. There's about 50 instructions. I don't know. I never counted on them. I never counted them really. The idea is it seems like a lot of instructions, but it's really not. The instructions are very similar. Once you start using some of them, you see the other ones is very similar. So here's all your instructions here. That's the instruction set. Here is the programming model. Okay, you're not going to need to know all this, or you need to know parts of it. But the issue here is the programming model represents the hardware that you, the programmer, can control. Okay, how do you control this hardware over here? You control it via the instructions. So you don't have control over everything. You have control over this stuff. So lastly here, here's your instruction set, here's your programming models, and this is the schematic of the computer itself. So obviously a bunch of more stuff in there. There's some of the stuff, you don't need to worry about anything now, but some of the stuff you will need to understand just because it represents the basic operation of a computer. Not a lot, but we're basically focused on programming in this class. And once again, this is the instruction set. Yeah, I could use the instruction set to control the hardware listed in the programmer model. And this is the entire schematic right here. And that's just the schematic over again. And essentially, folks, that's it.